all this started a while ago, after having been an investor and a manager and a consultant as well. I've been led to be concerned by strategic issues and strategic analysis and the limits of all this. It led me to elaborate, or to try to elaborate, a method around strategic intelligence. I became aware that when you deal with strategic issues, in fact, you have to deal with data. You need intelligence, you need expertise. And I had the intuition that it was interesting probably to try to gather all that. At the time, I wasn't aware about Bayesian network, and even less about BayesiaLab. So I tried on my own to find some solutions. And then I met virtually with Lionel and BayesiaLab, and I've been led to become aware that it was probably the good solution for me to handle these issues. And I had the chance to cross the road of the large company, meeting some huge strategic issues. They have tried to solve their performance issues with many kind of consultants, and they have been disappointed all the time. And I would say that they became desperate enough to consider that maybe what I could propose them could be a solution, and they decided to move forward with me on the work we'll try to introduce. I have some issues displaying my screen. I don't understand why. You can't see anything, I guess.
And now we can see your PDF display.
My
Now we see a PDF that says context and purposes.
Okay, good. That's fine. That's precisely what I want to show. So everything is okay. So yes, we started with this kind of proof of concept with a large multinational company, questioning itself about its 1,000 more branches network, with the purpose of trying to increase its own profitability and way of operating, because they have been losing market shares for a while, and they are trying to find solutions, and they don't know why. They don't know how to try to fix that. They decided to try to find new solutions, because they know that they will probably have to arbitrate between all of their branches, meaning that they have the feeling that they will have to maintain some of them, to close some others, maybe to create new ones, but they don't know on which basis they could make these kind of decisions, because they are not able today to identify within their branches what are the main characteristics of a branch that brings high performances, and what are the differences with some of the branches that underperform. And so I explained then that on the basis of Bayesian networks, neural network, and expertise, we could probably bring them some answers to these kind of questions. So we started to collect data coming from many sides of the company. This data came from HR departments, finance departments, which weren't used to be gathered together, because the company has very often, as far as large multinational companies are concerned, they are very siloed. Departments work on their own. They very rarely share data, and for the first time we proposed them to gather all this data, and obviously to use existing techniques so as to find correlations between all this data. And my friends and colleagues, Christophe and Emmanuel, will enter into details, but we started with 1 million data, and obviously we had to reach to some more treatable dimensions, so as to try to extract the relevant information we were seeking for, and I will transfer the speech to Emmanuel, which will start to enter into detail.
Okay, sorry. Okay, good morning, good afternoon, good evening, everyone. So I will share my screen now. That's okay. And yeah. Oops. Do you see my screen? Okay.
Yeah.
Yes.
Can you start the PowerPoint because we see all the item? Not just the slides.
Okay.
Yeah.
It's okay. Nice. Okay.
Yes.
So yes, we will have fourth part. So my part consists in the BayesiaLab in the process. So we will go from the empty missing zero dilemma, what I call, and then we will see an overview of PCM process and show how we will find causal results. For beginning, this is the upper left part of our data set. And this is reduced in Excel by squares, 1 pixel per 1 pixel. So you can have an idea of the data we have. And I have colored things in order to have this insight. So we had these kinds of values. And the question was, what does really this mean? When it is empty, it is different, that missing. When it is zero, is it sure it is zero or it was not an empty value, etc. And we had to treat the question to transfer it in statistics, where we have only missing and filtered alternatives. So as you understood in the talk before, it is not noise here, it is bias we are concerned with. And the question was how to do. So we had a job of a hard job, as Joel said. And in order to talk about filtered values, just imagine that you have a phone call and the connection is not always good. So there is two possibilities. You are in town and everybody around you or somebody's around you have a good connection and you don't. And other times it's the opposite. And if you are in this kind of landscape, you might be in the same situation, but at some moments, everybody won't have any connection. This is filtered values. If you want to know more about missing, this was done in Tuesday in Madeleine and Sueja talk. So with the filtered state in BayesiaLab, you can represent situations in which a node cannot represent a meaningful value given specific states of its parent node. So at the final, we had, so we begin with this initial data set, and with the final data set you have, we pass to 100 variables, to 1,000 variables to 100. But this work had different effects. You can see in the middle, it is a percentage of missing values that increase very, very highly. And the empty cells reduced to zeros because we made this job of resolving the dilemma. Yeah. What I want to do now is to emphasize something that is not always put first about BayesiaLab, that is power to integrate data. If you had this kind of data set, a small one, many softwares cannot go beyond this because they cannot treat filtered values, this NA, or missing. With BayesiaLab, you have this opportunity at start. You can define missing or NA. You can define the name of the missing values you have, the filtered values you have, etc. And you have this kind of small table. You have many information around. After it is color-coded, so in turquoise you have the to-be discretized variables, and the other are found as discrete variables by BayesiaLab. Then you have small statistics that can help you to see the kind of values you have and some insights. This alerts you that you have missing values there. And after, when you import the data, you have on the nodes informations, so a question mark to remind you that this node contains missing values, and the red funnel to remind you that there are filtered values there. You also have the possibility to have a dataset report. And one thing I saw that it was that we didn't have the number of filtered values there. So it could be interesting to have them in this table. Why do I want to speak about filtered values? Because this has an impact in the modeling you do. So in BayesiaLab, you can choose an option for removing filtered values. And in supervised learning, in unsupervised learning, you have these kinds of networks. So you can see the difference. And in supervised learning, this is quite different. You can see the impact here, a Markov blanket. This is not the same variable that is taken into account. So the way you define the variables and the way you consider them in your models have an impact on what you do. Why? Because of differences of perceptions. In one hand, you considered filtered values apart from your data at left, and in the right, you consider the filtered value in your data. So you can see that the MDL score is not the same. So the right node is more stressed, so we will want to connect in the network, and you can see the bias you introduce on your data. So the mean is double, and the standard deviation is very big. So after this quick overview, this is what we done for the PCM learning. So you have a phase of variable clustering. So this consists of creating clusters of variables. After you do your data clustering, your multiple data clustering, in order to find this kind of network. So the network you will work with is the upper part, and it's a resume of the manifest variables that are behind, so the first variable. And here I introduced our KPI, and we make an unsupervised learning in order to perform inferences on it. Some results, you can see here the total effects on our target. So this was very surprising for us to see that taux d'emploi. So how do you read this? You read that when you augment the mean of the variable, so the name of the variable as it are in the graphic at your right, when you increase their mean, the mean of your target decreases. So our target is a financial target we conceived. So you can see that the taux d'emploi, as the taux d'emploi increases, the financial rate, sorry?
Employment rate?
When the employment rate, sorry, if I traduce taux d'emploi, when the employment rate increases, our KPI, our financial KPI decreases. So this was very surprising for us. And we can see that the total effect, the most important variables in the total effect are around the market share, for market share and commercial and deployment. Then we can see in direct effects on target, these beautiful curves here. So the lecture is the same, but here when the mean of the variable increases, the mean of the target increases too for these four main variables you can see. So it's about, it helps to have insights about causal effects. We can go further in causal effects in order to find the contributions of the variable on the KPI. So the thing to know is that if for total effect there is no causal assumptions, that is, the information can flow from one variable to the target if there is an open path. For direct effects, they are computed by fixing the probability distributions of all the variables. So you can see that the direct effect is not important only for variables nearer from the KPI, but it can be important for variables far from this KPI, and negative too, and negative effects too. Well, we can think at this stage that we have done a great job, but we must remind and be modest in order that we only find one model amongst lots of ones, and that is where Christophe's work can come to help you with dimensionality, observation, and networks science. So I let the talk to Christophe now.
Yes, hello. I will share my screen if possible. This one. Can you see my screen with summary?
Yes, we can.
Yes.
Yeah, that's fine.
Okay, so we enter the subject. First, I will introduce myself. I am just a network scientist, one of the first French network scientists in 2009. Sorry. Yes. Network science was officially defined in US in 2006, so it's not an old science. We all know about data science, but network science is a specific branch, more specifically oriented on defining network representation as physical, biological, and social phenomena. So I know a little about Bayesian network because it's in network science as deep learning or over the neuronal network, but it's not my specialty. Anyway, we were in facing high dimension and space data sets. We have, for instance, on the left, we see...
Christophe, if I may interrupt
Yes.
you, we now see your screensaver, screen background. I'm sure you want to share your slide instead.
Yes. That's what I was asking at the beginning.
We saw it earlier, but then it switched to your background.
Okay, so because I have two screens here, and I suppose it's can I change here directly? No, I can't. So I will just change here. It's here. Can you see it now?
Now we can see it.
Yes.
I just want to. Excellent.
You see a big graph?
Yes, we do.
All right. I hope it will stay here. So you missed that definition?
Yeah, we didn't see that earlier.
Okay. So I was here. I started to speak about network science, which is a specific branch of data science oriented on network representation. And as a network representation, we get that at the first with about 670 nodes and 8,000 correlation pairs. Using a graphic clustering algorithm, we get 10 clusters. It's Blondel 2008 for the algorithm. And looking for correlation with Pearson coefficient above 0.5, we get correlated structure, which is more or less pairs. It was first. After we get we reduce dimensions and sparsity with just 6 times less nodes, but just 30% less correlated pairs. It means a stronger correlation between data and only 3 clusters where we get previously 10 clusters. So a better organization and less sparsity. We see the model we had before with high correlated pairs. It's also more core clustered. And if we continue, we can ask how. We see what, no how. We support the data elicitation using different algorithms available in Python, for instance, or the library. Here we get independence criterion from Hilbert-Schmidt algorithm. We still talk about independence first with Lionel, at the beginning of the talk of Lionel. And after that also we introduced automatic relevance determination, which is an interesting algorithm. Also, I will comment here at the before the ERD was giving a graph looking like this one. We first identified in red this little structure, for instance, and it was null because, in fact, this structure out of the main data mass was there were bad data after inspection examined from the expert, which is Joel in the domain. We saw that this data was mixing, for instance, the title was young people, and there were people having age 60 within this data, so it was irrelevant. We could, that's the way we detected it, and it will make it able to exclude that or on the reorganized data after reorganization based on the different visualization we get. We finally get a more clustered graph like this one. Here it's interesting because all the economic data are now aggregated with strong correlation links and relevance links. And in fact, it's bias, but an interesting bias. We could have used that as a similarity algorithm for determining similar terms, because if I have no right to disclose the exact name, but the exact variable names, if you could see, you see that they are little synonyms. They are all in the same semantic fields. And it would have been used for semantic aggregation, exactly the same. But here we just want to get relevant data, not semantic clusters. Here we get the market shares and the type of sectors activities which are also clustered. And here at the center we got what we could call noise, but we have also another interpretation. Sometimes here we find specific variables already identified as relevant by Emmanuel in the curves we just saw. So it could be a kind of a strong classifier that could be found here. We have not yet investigated with that because we are interested in first finding keynote structures. And this keynote structure, we found it. They are here using topology and flow-based search. These are specific algorithms using flows in the graph in order to, like maybe PageRank, which is a network science algorithm, not really used in Bayesian network, but in network science it's a very common algorithm with different variants. That's by the way, we use bridging centrality to get these ones, and we find here all the main activities and all the main different characteristic. It's kind of in French we say portrait robot. I don't know if the same in English are not the exact terms, but it's the main features. Representing all the other features. This is a generic features, in fact, extracted. And in terms of regressive analysis, we found also different, more balanced trees in regressive random tree forest. For instance, these are representative examples extracted from random tree forest regressor. Before we had this kind of structure, now we have more or less this kind of generic structure, more balanced. And we can find classifiers if, for instance, we segment the data with deciles and indeciles, in the first deciles and last decile here. Here we find various classifiers to weak, not really weak, here just weak, but most of them are easy classifiers. Not maybe the strongest one, but yet useful. Here, more in the last decile we have more weak classifiers, but anyway we get a branch here which might be interesting for Bayesian causation. How do we do to continue with our process? We have two other steps to pull signals from noise within that data set. First, we prepare the data set, reducing it to the essential things, eliminating noise, eliminating erratic variables, and we have now a more reliable data set, reduced, aggregated, and we want to extract and pull out noise from this data set, pull out signal from the noise in this data set. So we first use a GIS, an algorithm from Causal, which is takes a DAG, direct acyclic graph. It simulates interventions on the copy and search for Markov equivalence iteratively in order to give in output an essential DAG, or also called a CP DAG, conditional probability directed oriented graph. That I suppose you know in it should be also things that are implemented in BayesiaLab. And step 2, after that, from this essential DAG, we try to pull out signal from noise. Here we got in blue the noise, in green the more interesting signals. giving the essential graphs from step 1, and using another kind of P-rank, it's a prestige rank from Yan 2011. We page rank and using the prominent value, which is which can be in degree or half degree, and running all the graph, the pairs of nodes, we can find a global flows convergence, for instance, on these nodes, which is the global page rank, the higher rank global page rank for all the CPDEG. But when extracting that, we can see its local causation network. For instance, this node is this one, and we see here he is caused by things that are not in this local one, because these are over accumulation from over cause. In fact, it's a recursive accumulation of causes to consequence to causes to consequence, which is running upward, and in a way that PageRank work, we can say it's bottom-up approach for converging flows within the world graph, and after that we get the local community for this main cause. There are also other causes we have identified. And this main cause is here pairing with this local network of consequence and causes. It's also it is a cause for this here, and it is also influenced by its consequence. This cause is also one of the cause of this cause. So we are running up the tree of hierarchic causes in order to find the more essential ones within the essential CPDEG. That's the essential essentials. So to test our experiment, we first use visual comparison with our KPI, which is in blue here, and our detected causes, main causes. And for instance, in the last quartile, which is here, we found this. It's our top causes. It's in yellow, orange. It's mainly correlated. It appears to be correlated with the KPI, but in the third quarter, it was not. Here, with another example, we got in the first quartile a visible correlation with the KPI, which is relevant, and after that, always in the third quartile is not correlated, and even in the fourth one, we can see general correlation, but there are anomaly or irregularity, which indicates that it's not. It would have not. These causes would have not been chosen for the other quartiles, maybe for the second one, but it's good in the first one. Here in another one, we have a general inverse correlation with the KPI. That's the employment rate that Emmanuel was talking about. And we saw that finally it was a good candidate for the last quartile with general curves more or less following the KPI. Well, what we have to think is when we see local phenomena, it could be easy to observe with that kind of graphic representation, and we can find causation visually by exploration. But in certain cases, when we are in systemic causes, which are not strongly correlated with one or other variable, but which have globally a high correlation rate due to the world graph where we are in, it's not possible to observe comparing a pair it's not possible to observe just by a pair of comparing to the KPI with a variable. It's a pair. It's not easy to detect that this cause is influent, because it may be locally not influent, but globally influent. So you can't observe the global aspects in such graphs. You need such graphics. You always need to refer to the global graph and use network visualization to understand how it works in such a case. So we have isolated direct causes like this one, and other causes we call the systemic causes here. That systemic causes are not visually appearing with such representation. That's the trick. We have to understand where network science comes from, brings different tools on state of mind, on state and interpretation, and also reduce certain bias in terms of space of hypothesis that we have not with other approaches. Because it's especially interesting when we are talking about supervised elicitation, because in supervised elicitation, what we need is the machine to give us a set of causes that the expert would have not necessarily detected visually or intuitively. There were also Olivier Sibony was talking about intuition. You had to keep your intuition for the final phase and use the machine for the first phase. And I agree with this. We were talking about different subjects with him during the discussion, but anyway, it's true with that. Intuition is a flow in human judgment, and what we try to do using a global approach with deep networks and high combinatory models is to extract and pulling the weak signals from the noise as expected here. So thanks for your attention. I suppose it's Emmanuel to come back for the end.
Okay. Thank you, Christophe. Is it okay for you? Yes. Well, I can't. Yes. Oops. What is it? It's not the right page. So we are here. So Christophe spoke about well, why doesn't it? Yes, I will go to the end. Oops, I'm here. C'est pour ça le image F5. Yes, okay. So now it's our conclusions. So I want to emphasize in one thing as the first photo I show for the dataset. It is that we have done a reduction of dimensionality that is very impressive. At the beginning, we used unsupervised learning on our thousands of variables. And you can see also that unsupervised learning is a good way to make variables selection, because as the MDL score is conservative, you are sure that the nodes that are not connected are not correlated. Then we go to the selection of the resolution of our dilemma of variables, and we arrive to a thing like that. So you can see the reduction of dimensionality by 10, and at the end we add this PSEM well, there are the manifest node behind, but there is only 20 third factors. So we must keep in mind that it's a very powerful tool in order to get insights from data. And I think it's very interesting to have this in a simple picture. But we didn't do that for pleasure. We did that to provide a specific and a powerful tool to decision makers. We can give them decision trees. We can give them this most relevant explanation. So it's a way to get very quickly in the best insights, in the best states of the variables, to have the most efficient actions on the decisions they have to do. And then I will have 4 questions for you, and I don't know if we will have the time to respond to them, but I had the question if any one of you switched to the remove all filtered states option, and why. I have a question about variable clustering. Did you modify clusters composition that are proposed by BayesiaLab, and why, and what is the impact for you? How to solve convergence problems, because when we have to investigate with this kind of data very small parts of the KPI, there is some convergence problem, so you can improve the prior, but well, it is not so good. I think you are the MRO most relevant explanation tool also. So when you look at the console, you can have this warning message. How to explain in one sentence GBF? There were a very good talk of Michael Thompson 2 years ago, I remind. But the very question is, well, in one sentence, to explain to someone who doesn't know anything about statistics, what is a GBF? And I didn't succeed to find this way, because the base factor is very simple to explain. You have an hypothesis B, and you compare it to all, but the exclusion of the hypothesis is not very so easy. And I found something curious. Because I thought that the structural parallel learning, the meta learning, with more steps will be better than with less steps. And I tried, and I found that there was a kind of convergence to local minima, that is the SPL with the maximum weight spanning tree I did. I had this kind of things. The MDL was better for 40 steps. So I'm asking if it is due to the missing values, to the filtered ones. Well, if you have answers about that, I will be thanks. And I like the talk to Joel now for the last conclusion.
Thank you, Emmanuel. I guess indeed we'll have. I hope we'll have a few minutes for us to answer your questions. As far as I'm concerned, it won't be me, as you can imagine. Well, as a conclusion, I would say that in the end of this process, but in fact we are currently in the middle of the process as far as the large company we spoke about is concerned. And at the end of this, the feeling that we have in fact raised more questions than brought answers, and this is probably in fact what the global purpose. I mean, when the client asked us about how to spot a good branch to find some differences with a bad branch, in fact he asked us to treat and to process its data so as to raise issues. And it's the beginning, or we are in the middle of the iterative process, meaning that we have started to come back with him with some some answers, but in the sense we told him we need to investigate on these kind of relationships between two variables. We need to collect explanations about a correlation between two variables. And it's this iterative process that will allow us progressively to reach some conclusions and to identify some patterns that will bring him some answers. And in fact, it means that we need to involve experts within this process, because obviously, when sometimes we face some issues and questions and we are not able as far as to answer, because we don't know as precisely as the client, obviously, his field of work, and only his experts are able to bring some hypothesis about one possible correlation, or on the contrary, to say no, it's a dead end. There's no correlation between this and that, and so it means that there's still a process to achieve. But so far, we have the feeling that we have already brought some interesting issues and answers. We have helped the client to identify some performance patterns, to identify some reasons that can explain performance, and also to draw his attention on some characteristics they haven't noticed previously. And also, it was a side product, but we also identified some inconsistencies within their data, and outlined the fact that they face weaknesses as far as their data are concerned. And it means that at the end, at this stage, they seem to be happy with all that. And the next stage is to broaden the analysis, not only geographically, but also to integrate external data to the analysis we led, and which was precisely the global picture we had in mind at the beginning, meaning that we need to gather around the same Bayesian network some internal data, some external data, and all this should bring us to the possibility to release a decision-making model that could allow the client to make decision on some solid basis, and integrating more information than ever prior to make any decisions. And all this, I bet, will be allowed by BayesiaLab, obviously. Thank you very much.